Welcome to Introduction to Electromagnetism. This is lecture 1. Okay, for this lecture we have the following coverage. Review of Physics 1, which is Mechanics and Thermodynamics. Review of units and scientific notation. Introduction to charges. Types of charging. Finding the magnitude of charge. Okay, so let's start off with the review for Physics 1. Okay, so as we know, Physics is defined as the science of energy and matter. It is divided into the following subcategories. We have mechanics, heat and thermodynamics, sound, acoustics, optics, electromagnetism, and modern quantum physics. Physics lean on mathematics used to design apparatus for experiment. It provides the argument and states the conclusion. Physics uses the scientific method, which consists of experimentation, observation, recording, analysis, prediction, and confirmation. Standards and units. Any number that is used to describe a physical phenomenon, to quantify that phenomenon, is called a physical quantity. When we make use of a number to describe a physical quantity, it is essential to specify the units that we are using. So example, we have the quantity length. If we assign a numeric value to specify the quantity length, for example 25, we need to attach the units accordingly. So for example, the units meters, so we attach the unit meters to the numeric value 25 in order to fully describe a quantity such as length. Now we have the following basic units schemes. We have the FPS, the CGS, and the MKS systems. FPS stands for feet, foot, pound, seconds, whereas CGS stands for centimeter, gram, second. MKS stands for meter, kilogram, seconds. So this system makes use of the combination of the following basic units in order to quantify the following quantities of length, mass, and time. Now, of course, in the International System of Units, we make use of what we call prefixes in order to specify the degree of magnitudes or factors for a given quantity. So we make use of symbols in order to shorten the symbols for the prefixes. So here we have the following examples. So we have iota, zeta, exa, peta, tera, giga, mega, and so on. These are the set of symbols. Continuing, we have the kilo, hecto, up to yocto, and we have also the following symbols for each of these factors of magnitude. Okay, so let's proceed now with scientific notation. Consider the following numbers. We have 0.000000345. What is impractical of writing such numbers such as this one, or any number such as this one, 4786 followed by zeros to the left, is that it's too lengthy when you are writing it by hand. So instead of writing the numbers with using this lengthy notation, we make use of what we call the scientific notation in order to shorten the writing of the number. So in order to write a number using the scientific notation, we make use of the following rules. Okay, so if a number is less than 1, so for example, these numbers are less than 1. In order to write these numbers in scientific notation, what we need to do is to count the number of decimal places from the location of the decimal point, ending up to the right of the first non-zero digit. So for example, in this number 4786, 4 is the first non-zero digit. The decimal point should end up between 4 and 7. The idea is to have to express the number. The number should be expressed as a number less than 10. So meaning we need not to end up between 7 and 8 because it would end up as 47 and that number is greater than 10. So for practical purposes, we make use of a number less than 10 to specify the expression for scientific notation. So when we do this, we write down 4.786, if it is needed that the number should be rounded off, we round off that number. So for example, in this expression, the number 4.786 supposed to be, it was rounded off to 4.8. Now, counting the number of decimal places from the location of the decimal point ending up to the decimal place between 4 and 7, that is supposed to be 9 decimal places. When we move the decimal point from its location, moving the decimal point towards the right direction, that every decimal place corresponds to 1 degree of the magnitude of the exponent for 10. The movement of the decimal point moving towards the right corresponds to a negative exponent for your degree of magnitude. Now, if a number, on the other hand, if a number is a number greater than 1, so for example, if we have 18 billion, 18 followed by 9 zeros, so the scientific notation for this, any numbers greater than 0, the ruling is that you will be moving the decimal point from its location towards the left. Just the same what we have done in this set of examples. What we're going to do is to move the decimal places towards the left, ending at a number in such a way that that number would be a number less than 10. So we will not be writing the number as 18, we will not be writing the number as 0.18, but we will be writing the number as 1.8. Now, if the answer here is as an equivalent for this number is actually 2 times 10 to the 10, probably because it is needed that the number should be rounded off, just like what happened here. Instead of writing the number 4.786, it was rounded off to 4.8. So the same goes with this one. But actually, this could be written as 1.8 times 10 to the 10 if we need to specify the first decimal place to be significant. Okay, so for these last two numbers, for example, 1.6 times 10 to the 11, between these two and this one, between this number and this number, the proper expression for the scientific notation of this number is actually this one, 1.6 times 10 to the 11, instead of this one, which is 16 times 10 to the 10. So the idea here, although these two are simply equivalent, but the idea here is to make use of the rule that the number should be a number less than 10, the number that would appear here in the notation. Okay, so to continue, take note of the following examples. We have 2.15 times 10 to the negative 3. If we're going to express this or rewrite this number in the usual decimal form, we have 0.00215. Now, we can do this actually for numbers that are manageable enough in order to write down it into a shorter form. We need not to use the scientific notation for those numbers, but we only make use of the scientific notation for practical purposes, such as writing the numbers such as this one. So instead of writing it in the longhand, we make use of the scientific notation to shorten the writing of the number. Okay, so for this would start our discussion on the fundamental charge. This is actually the first topic on electromagnetism. Okay, so for this lecture, we have the following objectives. First is we need to define electromagnetism. Number 2 is we need to examine the nature of the electric charge. We need to study the 3 methods and types of charging. Now let's start off with the first objective, defining electromagnetism. So as you can see, electromagnetism is defined here as the study of electric and magnetic interactions. The interactions referred to here involves particles that has this property called electric charge. Now there are 2 types of charges that scientists have identified. One, they are labeled accordingly as positive charge and negative charge. The positive charge is actually carried by the basic elementary particle called the proton, and the negative charge is carried by the basic elementary charge called the electron. Now, so what is an electric charge? An electric charge is a physical property of matter. So, a physical property of matter, such as mass, is an inherent property of that matter. So the same applies for electric charge. An electric charge is an inherent property of all matter, meaning all matter has charges. Since all matter is composed of atoms, and atoms are made up of electrons, protons, since protons and electrons are the carrier of charges, therefore all matter is composed of atoms that has protons and electrons. Therefore all matter are electric charge carriers. So an electric charge again is a physical property of matter which causes it to experience a force when near other electrically charged matter. The standard unit of electric charge is called the coulomb, and this is written as capital letter C as an SI unit of, or the International System of Unit for electric charges. Now, let's proceed now with the types or methods of charging. Okay, so we have three types or methods of charging. We have charging by friction, we have charging by induction, we have charging by conduction. Okay, so let's discuss first the charging by friction. So, charging by friction is simply done by simply rubbing the materials, thus transferring charges from one of the material to the other material. So, example, when we rub a plastic rod with silk, what happens is that one of the charges becomes electrically charged. The same goes with the other charge because there is a transfer of charge from one of the other objects to the other. Another possible combination, for example, a glass rod rubbed with fur. Two plastic rod rubbed with fur. The two plastic. What happens when we rub two plastic when we rub a plastic rod with silk? What happens is that it acquires a negative charge. And for example, perhaps we have another plastic rod rubbed with fur. So when we try to establish an interaction between the two, what happens is that the two plastic rods repel. Whereas when we rub a glass rod with fur and the other one with silk, experimentally what happens to the glass rods is that also the two glass rods repel. So the point here is for something such as plastic rods or glass rods to repel or to attract or is one way for them to acquire a charge is simply by rubbing them together. So such as when we do the rubbing together of plastic rods with silk and glass rods with fur. Now, the possible combination of the type of interaction that would happen between the plastic rods and the glass rods is any one of the following possible interaction. One is when one charge object is negative and the other one is also negative. What happens to these two when they interact is that they would repel. The same goes when glass rod acquires a positive charge, and when they are interacted together, what happens to them is that they would also repel. The same goes with what happens to the plastic rods. Now, another curious thing that what happens to this experiment between rods and glasses is that when you try to establish an interaction between the plastic rods and the glass rods, is that instead of repulsion, what happens is that the plastic rods is actually attracted to the glass rods. Therefore, this experiment establishes a basic interaction of nature that happens between charges, which is only of two types. It's either the interaction is either a repulsion or an attraction. So by this scheme, we can actually conclude that whenever two charges repel, they repels in such a way that they have the same charges. So we say that same charges repel. And on the other hand, when two charges have opposite charge in them, what happens to their interaction is that the type of interaction that would happen is that they attract. So therefore, we conclude that whenever two charges have the same sign, they repel. When two charges have opposite signs, they attract. So as we can see in this illustration, that the person in the background is actually rubbing a plastic rod with a cloth. The cloth is actually fur. So what happens to the plastic rod is that it acquires a certain amount of charge, enabling it to attract pieces of paper on top of the table. So this would not happen unless that the plastic rod is actually is equipped with charge. Okay, so then therefore we arrive with this conclusion that whenever two positive or two negative charges establish an interaction, and that interaction would actually a repulsive interaction. And whenever a positive charge gets near a negative charge, what happens to these charges in terms of interaction is that they would attract each other. Now take note, like charges doesn't mean that the two charges are identical, only that they have the same algebraic sign, as in one is positive and the other one is negative. Okay, so let's proceed now with charging by induction. So the charging by induction, this is actually a method used to charge an object without actually touching the object in the object to any other charged object. As illustrated by this picture, on the first diagram you have two metal spheres that are mounted on insulating stands. So these are the stands. On this diagram, they're actually touching each other. The idea here is that the touching of the two metal spheres, that means that they are actually sharing the charges that are present on both spheres, both sphere A and sphere B. Now, on the second diagram, in the system, it was introduced an object that is charged. In this illustration, that object is actually negatively charged. So what happens to the presence of the charges in the two metal spheres is that, since the idea is that opposite charges attract, what happens that the present positive charges on two spheres actually moves towards the direction of attraction of the object that was introduced. Therefore, we will have an accumulation of positive charges on one of the metal spheres, particularly on this side of the sphere, on sphere A. Now, also, since we have established previously that negative charges repel, at the same time that the positive charges are attracted on this side, the negative charges are actually repelled towards the other end of the sphere on sphere B, since they are being pushed away by the introduction of this negative charge. Now take note that the introduction of this negative charge does not necessarily need to touch the two metal spheres. So just like what is said in the idea of induction, that the induction process does not need that the two objects are actually touch each other. Now, on the third diagram, what happens now here is that the two spheres were separated from each other. So meaning that we are able to isolate the positive charges on one of the spheres, particularly the positive charges on sphere A and the negative charges on sphere B. Thus, we have an isolation of charge on the separate spheres, sphere A, positive on sphere A and negative on sphere B. And this process is called charging by induction. Okay, so next is the third process of charging an object. We call this charging by conduction. Okay, so the idea of conduction is that there is a need for the two objects to be touching each other, just like when we do this charging by friction. It involves contact, physical connection of the charged object to the neutral object. Okay, so in the first diagram, we have here a metal sphere with an excess of a positive charge, just like what we have done in the previous example on induction. What happens now here is that the sphere was brought near to a neutral electroscope. An electroscope is actually a device wherein you have a suspended metal foil, and this metal foil is actually represented by this line, gray line. So upon contact on the electroscope, what happens is that the negative charge was acquired on this part of the electroscope, which causes the metal foil to rotate about an axis. This happens, of course, because the mounting of the metal foil here acquires a negative charge from the contact between the metal sphere and the mounting. What happens is that the charges was transferred both on the mounting and the metal foil. Thus, since the metal foil is free to rotate about its axis, and the mounting is also of the same charge, and these two charges would repel each other, since the repulsion would push the metal foil. This would cause actually the metal foil to rotate about its axis. Okay, so this is the charging by conduction. Now let's talk about the law of conservation of charge. This law states that the number of protons is equal to the number of electrons for any neutral atom. This is the basic idea. A neutral atom is basically composed of equal numbers of protons and equal number of electrons. So for example, a hydrogen atom, the hydrogen atom is the simplest of all atoms. It is composed of one proton and one electron. So all neutral atoms have the same idea. For any given neutral atom, the number of protons is equal to the number of electrons. Determining the overall charge of the system is simply a basic idea of arithmetic of adding and subtracting, particularly the number of electrons. Take note, it is the number of electrons that we count in order to specify whether an object would charge up to positively or would charge up negatively. So the idea is simply to get the sum of the charges on the individual spheres, or for in this case, in our example, individual atoms. Okay, so for example, we have the overall charge of the two spheres as positive 1,000 units of charge plus a negative set of electrons comprising of negative 1,000 units also of charge. Then the net charge, we say that when we add them together, would be of 0 units. Since the number of positive charge and the number of negative charges equal each other, therefore it is said to be that the object has no net charge or 0 net charge. Now let's talk about the importance of ground in induction. Sphere B acts like a ground. Remember in our diagram, sphere A acquires a positive charge. Here, sphere A actually acquires a positive charge and sphere B acquires a negative charge. Now take note, sphere B acts like a ground. The ground serves as a large object that is infinite source of electrons, or sink for electrons. So literally, when we say ground, just like in electrical installations, when try to notice, for example, from in your household, that whenever you ground your house, your electrical connection from your house is actually grounded. There is a wire coming from the post entering your house, which is basically grounded towards the ground, literally the ground. Because the idea of the ground is that the ground serves as a large sink for electrons. So just like what we have done in the process of induction, the second sphere, which is sphere B, acquires the negative charges and serves as the ground for the process of induction. Okay, so let us try to illustrate again the process of induction. So we have here one of our original metal spheres mounted on an insulating stand. We again introduce a negatively charged object so that the positive charges on the sphere would accumulate at one side of the sphere. The negative charges would accumulate at the other side of the sphere. Now, what happens now if we're going to touch one side of the sphere, particularly on the side wherein the negative charges accumulates, and and we s- this process, we actually call this process as grounding, or we say we ground the sphere. Now, what happens now here is that the sphere is now positively charged since we have removed through grounding the negative charges that were accumulated at one side of the sphere, leaving the original sphere an excess of positive charges, so making the sphere positively charged. Now, let me introduce to you the idea of the fundamental charge. Okay, so let's have this formula, Q. Q here represents the total amount of charge that is either acquired by the object through friction or through induction or whatever process. Q here represents the overall net charge of an object. Counting the overall net charge is actually a function of the number of electrons. Here, E represents the charge of 1 unit of charge, which is the charge of the electron. N represents the number of charges or the number of electrons. Q would be the magnitude of charge expressed in coulombs. And again, E is the fundamental electron charge. And take note, the fundamental electron charge has this value, 1.6 times 10 to the negative 19 coulombs. So that means every object that has acquired a net charge is actually a multiple of this fundamental value, which is the value of the charge of one electron. Okay, so for example, if you have 16 million electrons that were removed from a neutral sphere, what is asked in the problem is that we are asked to find the magnitude of charge that was gained by charging the object. So the answer is actually 16 million electrons that were subtracted. The object would have gained an additional 16 million units of positive charge, equivalent to the number of electrons that were removed from the neutral sphere. Therefore, the overall charge of the neutral sphere would now be positive 16 million coulombs. Okay, so that ends up the lecture for the introduction of lecture 1. I am expecting that you will be able to answer the check for understanding. Kindly answer the numbers up to the end of the slides. Submit this on Friday, April 14.